So, hello everyone. Last class we have discussed that d orbital splitting in octahedral and tetrahedral field, right? Tetrahedral field. I told you that in presence of ligands, d orbital are split into two different sets, T to G and Eg in case of octahedral field, and E and T2 in case of tetrahedral field. Now, this splitting energy, that is called delta, this splitting energy depends on some factors. Okay. So first we will discuss the factors on which this splitting energy delta depends. Okay. So today, first we will discuss that what are the factors on which the splitting energy depends. Our first factor is the number of ligand and geometry. Number of ligand means already we have discussed that in case of tetrahedral field there are 4 ligands, 4. In case of octahedral there are 6 ligands. When there are 6 ligands, more interelectronic repulsion, so gap is very high. When there is less number of ligands, there will be less interelectronic repulsion. Repulsion means repulsion between the electrons present in the metal and electrons of the ligand. Okay, when there are 4 ligands, repulsion will be less. When there are 6 ligands, repulsion will be more. So, number of ligands is a factor that will affect the delta or splitting energy. So, delta will be proportional to number of ligands. Okay, so therefore, in octahedral delta O means splitting energy in octahedral field is greater than delta T means splitting energy in tetrahedral field. Another thing is also important, that is the geometry. If we compare the splitting energy of tetrahedral complex and square planar complex, both are actually ML4, right? Tetrahedral and square planar in both are ML4, means 4 number of ligands. But in case of square planar, the splitting energy will be very high. Okay. Since square planar complex is not in your syllabus, I am not discussing. But remember that the splitting energy also depends on geometry. When both cases same number of ligands like tetrahedral and square planar, in both cases there are 4 number of ligands. But in square planar complex, the splitting energy is high because in case of square planar complex, all ligands are coming along the axis. Next factor is the nature of ligand. Last class I discussed what is spectrochemical series. So, nature of ligand means some ligands, I already told, ligands where the atom has less electronegativity, and there are some atoms there has more electronegativity. When we have atoms having more electronegativity, it will be called weak field ligands, and whenever it has less electronegativity, it will be called strong field ligands. So, nature of ligands is an important factor. Depending on ligands, the splitting energy depends. Means if we have fluoride is a weak field ligand, and cyanide, this is a strong field ligand. So if we have strong field ligand, now we can come here. Okay, if we have strong field ligand, the splitting will be high, right? If we have weak field ligand, the splitting will be less, right? Last class also we discussed. If we have d orbital, it will be split into 2 sets in case of octahedral field. Now splitting will be less if we have weak field ligand, splitting will be high if we have strong field ligand. So here I have written for weak field ligand fluoride, strong field ligand cyanide. Okay. So second factor is nature of ligand. So in the spectrochemical set, all the ligands on the left hand side are weak field ligand, and ligands on the right hand side are strong field ligand. Okay, so depending on the ligand, it is delta depends. Okay, now these two is called the ligand factor and geometry factor. Now I will discuss the metal factor. There are 3 metal factors. Metal factors that depend, that influence the crystal field splitting. Okay, that influence this crystal field splitting. So first factor, metal factor, is oxidation state of the metal. Okay, oxidation state of the metal is the first metal factor. Means if the oxidation state is increased, then crystal field splitting also increase. Now in that case I want to say this crystal field splitting that I told you that depends on inter-electronic repulsion, it also depends on some electrostatic interaction between metal and ligand. So if metal has very high positive charge and ligand is always negative charge, then high positive charge and high negative charge, the interaction will be much more. So whenever ligand has very high positive, metal has a high positive charge, the splitting will be increased. The electrostatic interaction between metal and ligand, it will increase. So this splitting, it is not only depend on the inter-electronic repulsion, it also depends on the electrostatic interaction between metal and ligand. So when I am talking electrostatic interaction, electrostatic. So electrostatic interaction between metal and ligand. So if the metal and ligand electrostatic interaction increases, then also this gap will increase. So therefore, when metal has a very high positive charge, the electrostatic interaction will be plus and minus, it will be high. So the delta value will increase. So therefore, as an example, we can say iron FeH2O6 2 plus, the delta value is 10,400 centimeter inverse, and when we are taking 3 plus complex FeH2O6 3 plus, delta value is 13,700 centimeter inverse. Okay. So delta depends on proportional to oxidation step of the metal. Fourth one, delta depends on quantum number of the d orbital. Whatever d orbital means, we have 3d transition metal, 4d transition metal, 5d transition metal. So transition metal having different d orbital, 5d, 4d, 3d. So if the quantum number of the d orbital is increases, this electrostatic interaction is also increases. Because of that, the delta value is increases. So therefore, delta for 5d will be greater than delta for 4d and delta from the 3d. So as an example, we can take these three complexes. One is cobalt, rhodium and iridium. Cobalt 3d, rhodium 4d and iridium 5d. In case of cobalt ammonia complex, delta value is 23,000 centimeter inverse. In case of rhodium ammonia complex, value increased to 34,000 centimeter inverse. And in case of iridium complex, delta value is 41,000 centimeter inverse. So delta is depending on the quantum number of the d orbitals. Now last one is delta is inversely proportional to number of d electrons present in the metal. Number of d electrons of metal. Okay. So if the metal having more number of d electron, delta value will decrease because electrostatic interaction will decrease. Now we can take two examples. One is cobalt water complex 2 plus, nickel water complex 2 plus. Both have same positive charge 2 plus 2 plus. But in cobalt it is a D7, 7 number of d electron. Nickel is a D8, 8 number of d electron. When there will be more number of d electrons, so delta value will be decreased. So you can see in case of cobalt, delta value is 9,300 centimeter inverse. In case of nickel, delta value is 8,500 centimeter inverse. Okay. So these are the 5 factors are important that will depends, that means that will affect the splitting energy. Okay. Next I will discuss the calculation of CFSE value. Okay, I have to erase this part. And I have to show you that how we can calculate the crystal field stabilization energy. CFSE means crystal field stabilization energy. How we can calculate crystal field stabilization energy we will discuss in this class. Okay. So we have to discuss the crystal field stabilization energy calculation for tetrahedral complex, and then we will discuss octahedral complex with one high speed and low speed. So I am erasing this part, and next we will discuss the calculation of crystal field stabilization energy. So already we discussed that splitting pattern, already we know. So if there is some electron in case of tetrahedral, first we will discuss in case of tetrahedral. tetrahedral, TD. So our formula is number of electron into energy. Now if we, for example, if we take D1 means, if we take D1 means one, there is one electron present here. Now in case of tetrahedral, these electrons will come to lower energy level here. Right? So CFSE value for D1 system it will be CFSE value for D1 it will be, so number of electron is 1 into energy value here, the energy value is minus 0.4 delta T. So minus 0.6 delta T. Okay. And EG level there is no, and T2 level there is no electron, so there will be no energy. So this one plus 0. Okay. This is our E level, this is our T2 level. T2 level is 0. So total CFSE value will be, CFSE value for D1 it will be, so minus 0.6 delta T. Right? So CFSE value for tetrahedral complex D1 minus 0.6 delta T. Now if we have 2 electron D2, if we are calculating for tetrahedral complex. Okay. So this is CFSE value. Another thing also we have to calculate the magnetic moment, right? Magnetic moment mu. So magnetic moment mu means number of unpaired electron. Number of unpaired electron. Unpaired electron means there is one unpaired electron. So magnetic moment mu will be root over number of unpaired electron 1 into n1 plus 2. Means if we calculate, it will be 1 into 1 plus 2 means 3 root over 3. Root over 3 means if we calculate, we will get the value. It will come around 1.73 Bohr magnetron. Okay. Now come to the D2 system. D2 system means there will be 2 D electron. Right? There will be 2 D electron. 1, 2. So now the second D electron, it will come here, lower energy level. Right? So now for D2 system, number of electron in E, it will be 2 electron into their energy is minus 0.6 delta T. Okay. Plus in T2 level there is no electron, so no energy is 0. So overall the CFSE value, this is our CFSE value. CFSE value will be minus 2 into 0.6 means minus 1.2 delta T. And magnetic moment value will be, mu value will be root over, we have 2 unpaired electrons, 2 unpaired electrons, so magnetic moment value will be root over 2 into 2 plus 2. Right? It will be root over 2 plus 2, 4 into 8. Right? Root over n into n plus 2. Here n is the number of unpaired electrons, 2 plus 8. Okay. So in that way you can calculate magnetic moment value. Now if there are 3 d electrons, in case of D3, the CFSE value will be D3 means it's the third electron. Now this third electron, it cannot come to the E level because E level is filled. Now it will go to the T2 level. Right? Now this CFSE value will be number of electrons in the E level is 2 into minus 0.6 delta T. Completed. Now in T2 level we have 1 electron plus in 1 electron in T2 level 1 into plus 0.4 delta T. So overall value will be minus 1.2 plus 0.4 equal to minus 0.8 delta T. Right? Minus 0.8 delta T. Okay. So in that way we can calculate the CFSE value. Okay. Now for D4, D5, D7, D8, these are the important, because of that I am written. So CFSE value for D4 system CFSE value will be, now if we take D4 system, so D4 system means this one, number of electrons 4. So 4 means fourth electron will come here. Right? Fourth electron will come here. The same way, if we calculate CFSE value, it will be minus, first CFSE value for D4 system. So we have to write E and P2. In the E level, number of electron will be 4. E level there will be 2 electron into minus 0.6 delta T plus in T2 level there is again 2 electron, 2 into 0.4 delta T then total value will be minus 1.2 plus 0.8 will be minus 0.4 delta T. Okay. So like that you can calculate the CFSE value for D4, D5, D6, D7. Now if we come after, if we check that CFSE value for D6 system, D6 means, okay, D5 I am not calculating, you can calculate, it will be the same way. Now D6 system, D6, okay, D6 means there are 5 electrons, now extra 1 electron here, right? Now this extra electron, so 5 electron means 5, now 6 electron it will, so all are half filled, now 6 electrons will come here in the E level, lower level, right? Now total number of electron will be, in for D6 system, CFSE value will be, same way you can calculate, now E level total number of electron is 3, here is the 3, right? So for D6 it will be so 3 electron in E level, 3 into 0 minus 0.6 delta T plus 3 electron is present in the T2 level, 3 into 0.4 delta T. So overall will be 3 into minus 6 means minus 1.8 delta T plus 3 into 4 means 1.2 delta T. So it will be minus 1.2 minus 1. So minus 0.6 delta T. Right? Now if we have to calculate magnetic moment, so in this case number of unpaired electrons is, we can't we can't take these 2 electrons because these 2 electrons is not unpaired. Now here number of unpaired electrons is 1, 2, 3, 4. So here number of unpaired electrons is for D6, N value, number of unpaired electrons, it will be 4 only. Although there is a 6 number of electrons, but these 2 electrons spins are opposite. So one spin will cancel another spin. So we can't take these 2 electrons for magnetic moment. Because whenever there is a single electron, then that single electron when moving, it is generating magnetic moment. If there is another electron in the same room, then this movement of this electron is opposite. Opposite means opposite spin means opposite magnetic moment. So one magnetic moment will cancel another. Means if it is, let's say it is North Pole, South Pole, it will be North Pole, South Pole, then it will cancel each other. So from these 2 electrons we will not get any magnetic moment, so we cannot take these 2 electrons. So for to calculate the spin only magnetic moment for D6, we have to take only 1, 2, 3, 4 electrons, so N equal to 4. So mu will be root over N into, means 4 into 4 plus 2. Okay. So in that way you have to calculate the spin only magnetic moment.